Hello students, in the previous lecture we discussed up to is Biot Savarts law statement and its scalar and vector form. Today we are going to continue that content. Okay, yes, please see that for your continuation, so I will recall that Biot Savarts law. So Biot Savarts law. What it says, you just consider some conductor which carries the current I. There is a small element of length dl, whose how we consider area as a vector in Gauss law. Similarly here also the length is considered to be a vector quantity whose direction is given by along the tangent in the current direction. Okay, so now please see that this is the measuring point P. So which is the point where we have to measure the magnetic field due to the small portion of the wire. Okay, so let R vector be the position vector. Yes, the angle between position vector and this current element or element length element is theta. So then this law, Biot's law gives that dB is equal to mu naught by 4 pi ideal is sin theta divided by r square. So this is the a scalar equation what we used, and where mu naught will be a constant 4 pi into 10 to the power of -7 Henry per meter. So this is the data what we discussed in scalar form. Already we are given vector form also. So now we continue this applications of Biot Savarts law. So the application of Biot Savarts law. So in this we are going to derive the expression for a magnetic field due to a current carrying circular loop or coil. Yes. So now please see that there is a circular coil of radius r, where the point P is called axial point, where we have to measure the magnetic field due to this current carrying circular loop which is at a distance x. So let us consider a small portion length element dl, and we are assuming that current is going in anti-clockwise direction. So therefore the tangent direction will be like this. So this is the tangent direction. So the point, the line which connects the element and the point P is nothing but position vector. So therefore here we can write that this small r will be the position of the point P from this current element, whose value is given by, this is the right angle triangle. Say this is some point C, something like that. Then OPC is a right angle triangle. So in that we can use the Pythagoras theorem to get this. This has to be r square plus x square, and this angle is taken as to be some angle alpha. Now please see that student, the radius and tangent always makes the 90 degree angle. Therefore this angle will be 90 degree. So therefore in this case theta is 90 degree. What is theta here? The angle between current element and the position vector. Therefore the sin theta value in this case will be therefore sin theta value in this case will be 1. So this is the first thing what we keep in mind. Now please see that since when we write the vector form, kindly remember the vector form of this one, dB vector is equal to mu naught by 4 pi ideal vector cross r cap divided by what, children? R square. So whenever a cross product comes, I asked you to apply the right hand thumb rule. So here also the dl vector is rotated towards the r vector, that is r cap. So this cross product is always perpendicular to the plane of dl vector and r cap. Please kindly remember that. Therefore this this will be the magnetic field, say dB vector, which makes the perpendicular to the plane contained by dl and r vector, which makes an angle alpha with respect to vertical. Now this vector component is resolved, this vector is resolved as component. This will be dB cos alpha and this will be dB sin alpha. Okay. So similarly you just recall, you just consider a diametrically is opposite element. So this is dl. So diametrically opposite element. So this will be given as to be like this. And this element, due to this lower element, the magnetic field is produced in this direction. So this is another dB vector. So which makes angle as alpha with the as vertical, as since that is diametrically exactly opposite to that. So therefore this is alpha. Now again you resolve, this has to be component. This will be dB cos alpha and this will be dB sin alpha. Since the same current is passing through that, the value of dB is constant. Therefore this vertical component dB cos alpha gets cancelled out. Therefore the only survival component will be dB sin alpha acting along the horizontal line or along the axis of the coil. So therefore I can say that the total magnetic field is nothing but the summation of the survival component, that is dB sin alpha, dB sin alpha. Okay. Now please see that what is this dB value. So you see that from this equation, as we said here, sin theta is 1. Therefore I can write that dB is equal to mu naught divided by 4 pi ideal divided by r square. This is dB value since sin theta is 1, as we said here. So therefore the substitute that is r square, r is there root over r square plus x square. Therefore you can use r square also. Therefore I can get as b is equal to integral is dB value mu naught I divided by 4 pi r square into dl into the sin alpha value. The sin alpha from this right angle triangle, I can say that this is the right angle triangle OP is some point C, x this will be r. So this is alpha. So this value is root of r square plus x square. Yes. Now please see that capital R square, that is equal to small r. So now you please see that sin alpha r by small r. Therefore this will be r divided by small r. Yes. So therefore I can get b is equal to mu naught I r divided by 4 pi r cube integral dl. So what is r? R is nothing but, so therefore here you see that r is nothing but x square plus capital R square, that 1 power as a whole power 1 by 2. R cube means you just write the power 3. So therefore we can get r cube has to be as x square plus capital R square whole power 3 by 2. So now substitute here. Now please see that this is the integration value. Whenever the element is integrated, you can get the circumference of the as a loop. Therefore I can get this total integration value is circumference of the coil. So now please see that, children. So therefore we can write b is equal to mu naught I r into 2 pi r divided by, so 4 pi r cube is nothing but capital R square plus small x square, that is x square 3 by 2. Okay. So now please see that, or we can write that b is equal to mu naught I r square divided by 2 into r square plus x square whole power 3 by 2. So this is the required expression as for the as a current carrying circular loop. Okay. Now please see that if this coil contains n number of turns, then we can write that the total, if there is n number of turns, so n number of turns, then the total magnetic field produced is B is equal to mu naught Ni, total current, into R square divided by what, children? 2 into R square plus x square whole power 3 by 2. So this is the information related to as a circular coil. If n turns are there, you just multiply that expression with n. So here, since B is the vector quantity, how to find out the direction of B vector? So in the case of circular coil, you just use the right hand as a palm rule. Yes, you just hold the coil in your hand, in right hand. The curling fingers represents the direction of current flow in the coil. Then thumb represents the direction of the magnetic field. So therefore, to find the direction, so I can use right hand palm rule. There are many rules. So right hand is a palm rules. What is this right hand palm rule says? Just to see that the curling fingers, curling fingers current direction. Curling fingers, what children? Current direction. Then the extended thumb will gives the direction of magnetic field. So the thumb will gives the thumb finger will gives the B vector direction. Okay. So this is the way how to find out the direction in the case of circular coil or circular loop, whatever may be the cases. Here also I can discuss some special cases here. Just to say this is equation number 1 and 2. So from this equation number 1, if x equal to 0, what is x here? The distance from the center of the coil. So if the point P is at the center, then x equal to 0. Therefore at center, then what this expression gets simplified means this becomes to 0, then r cube, so it gets cancelled out. Then B is equal to mu naught. Suppose n turns are there, you just write n, or a single turn means you just write I. So divided by is a 2r. So this is the maximum value. This is the maximum value of the magnetic field produced by the circular coil. Okay. So since the coil has we can measure the right side or left side. So therefore when you draw the graph for this expression, this case, just to see that this may be the positive x value, negative x value. That means the right side of the circular coil, left side of the circular coil. Therefore the graph will be like this. So there will be a maximum. This is B center. So this is the value of B. So when we are moving away from the center of the coil, the magnetic field decreases. So this is the information related to a circular coil magnetic field. And moreover, you just see that what is the magnetic field produced by the circular coil. So let us assume that this may be the circular coil is carrying the current, so in this direction. So this is the current. As we said, you just apply the right hand as a palm rule. Just the fingers gives the direction of current, then thumb will gives the direction of magnetic field. So therefore, in this case, for this circular coil, the magnetic field will be like this. Yes, in this pattern we will get. So this will be the direction of magnetic field produced by the circular loop, children. So this is the information about the magnetic field due to a circular coil, which is one of the application of Biot Savarts law. The next what we are going to discuss is that is another important concept like our Gauss law in electrostatics. That is nothing but Amperes circuital law. Amperes circuital law. Amperes circuital law. So what this law says, the line integral of this integration, L represents line, the closed circle represents, we are considering a closed path. Okay, the line integral of B vector dot dl vector, that is equal to mu naught times I enclosed. Mu naught times what, children? I enclosed. For example, you just consider some random what is that as imaginary Amperian loop. So let us consider there are certain currents which are going outward, some currents which are going inward directions. Okay, like this. Say for example, this is I1, I2, etc. I3, etc. Now please see that as we discussed in Kirchhoff's law, we are using the sign convention. In Gauss law also, the inward flux is negative and outward flux is positive. Like that, here also we can say that the currents coming inward is negative and currents going outward will be positive. Therefore, I enclosed is nothing but the sum of the current enclosed by this Amperian loop. Imaginary that closed loop is called Amperian loop. So this is the I enclosed. As we discussed in Gauss law, how the Gauss law says the charges lying outside of the Gaussian surface is not accountable in the Q enclosed. Similarly, if any currents lying outside is need not to be considered. Any current lying outside of the Amperian loop, the current need not to be considered in the I enclosed calculation. Okay. So or the same dot product, we know the property of dot products. So for your mathematical note, I can say that please be careful with that. So A dot B, so that is equal to AB cos theta, and A dot B is A dot B is commutable, so that is B dot A. We can both are same, and it is a scalar quantity. And moreover, for a similar pair of unit vectors I dot I, J dot J or K dot K, the value will be 1. For dissimilar pairs, that will be 0. And another one is, if the A and B are given in component form, like AX I cap plus AY J cap plus AZ K cap, like this A vector and B vectors are given, then we can write the as a dot product in the form of as A dot B. We can say that A dot B for the component form, just a similar pair only will survive, the remaining pairs will be 0. Therefore AX BX plus AY BY plus what children? AZ BZ. So this is the mathematical note what we must know, since we are using dot product here. So therefore we can expand this integration and we can write the yes. Now please see that we can say is line integral BDL cos theta, that is equal to mu naught I enclosed. You please see that the cos theta means the angle between magnetic field and the current, that length element what we consider here. Okay, so this is the scalar form and this is the vector form of the Amperes circuital law. So using this, when compared to Biot Savarts law where we did the lengthy derivations, that Amperes circuital law will reduce that mathematical work, and it is easy to get the results in the simple steps. Now the first application is, applications, the first one is magnetic field due to a infinite long straight wire. So B vector due to infinite long straight wire. Infinite long what children? Straight wire. So just to see that this is the infinite long wire, and you know that the magnetic field is upward, means the current is upward, means the magnetic fields are makes the concentric circles. So this will be the is a magnetic field pattern. So say for example this is so at any point P whose distance is r from the wire, we have to measure the what is the magnetic field due to this current carrying system. So now please see that you just imagine a Amperian loop whose radius is r, and since the direction of magnetic field is concentric circle about the wire, therefore it is acting the direction of any part, anything moving along the circular part can be obtained by drawing a tangent direction. So this will be the direction of B vector. So similarly, let us consider, since this is an Amperian loop, the direction of element is in the along this direction, dl vector also along the same direction. So this is the position of the wire I, which carrying the current. Okay. Now in this case, both the B vector, dl vectors are in the same direction, therefore theta equal to 0, therefore cos 0 equal to what children? Cos 0 degree equal to 1. Therefore I can write that as a line integral BDL cos theta, as this cos theta is 1, therefore closed integral BDL, that is equal to mu naught. The total current enclosed by this Amperian loop will be I. So this is I. Or B, in a small region we can consider B as to be constant, therefore we can say that is line integral of dl, that is equal to what children? Mu naught I, and this is the circumference of the coil, therefore we can write that as B into this value is a circumference of the Amperian loop of the radius r. So the 2 pi r, that is equal to what children? Mu naught I. So from this I can say that B is equal to mu naught I divided by 2 pi r. So when compared to the lengthy derivation did by in a straight wire, infinite long straight wire or finite wire, it is easy to get the relations. So here you just see that B is inversely proportional to r and B is directly proportional to I. So when you draw the graph, Yes, you know that you learned the basic mathematics. The graph will be a rectangular hyperbola. Suppose as the graph is drawn between B and R, the distances. And sometimes they may ask you what is the difference between B and as R. It may be R or R square, something like that. So that and all very important for your discussion. Okay. So in this case, when the current is passing through the straight wire, how do you find the direction of magnetic field means the same thing as you just apply the right hand as thumb rule. Here in this case, thumb points the direction of current and the fingers points the direction of the magnetic field. So please be careful about the rules where and which fingers represents what quantity. Okay. So the second application what we are going to discuss is a solenoid. Yes. So solenoid is a magnetic field B vector due to solenoid. This is the second application what we are going to discuss. Magnetic field due to due to current carrying solenoid. So okay, so this is even whether it is there in CBSE or not, but we need it for MCQ purpose. So therefore, you please kindly learn this. So what is solenoid means? A solenoid is nothing but a insulated copper wire which is winded in the form of a helical shape, in the form of like this. Is you have to be drawn. Yes, in this manner you have to draw. So let us consider some current I is passing through this as a solenoid of length L. Okay, is length L. Now please see that the number of turns in the unit length, as we discussed in current electricity, small n represents number density, number of free electrons, total number of free electrons by unit volume. So similarly here also small n is defined, that is nothing but number of turns per unit length. Number of turns per what, children? Unit length. Okay. Now please see that this is the first thing what we must note. And since the windings are very closed with each other, for understanding purpose I drawn little bit more gap, but in practice it will be very closed one, like our spring. So it is due to that, due to the closeness of the windings, we can say that the solenoid is nothing but the cross section of the solenoid is nothing but a thin sheet. So therefore, you just see that this is the cross sectional view of the solenoid, which is treated as to be a thin sheet, since due to the closeness of the windings. As we discussed earlier, the cross means the current is inward, and the dot means the current may be outward. So let us assume that the current is going inward direction. That means in this manner the current is going. Therefore, here the current is inward directions. The current is what, children? Inward direction, and there the current will be outward. So top layer it is current is going in, and as outer layer, that the lower layer it is coming out, for example. Okay. Yes. So now please see that this is the way. So current is going inward in the top layer and coming out in the bottom layer. It is going like this. So because of that, we can represent the current as to be like this. Let us consider in the case of solenoid, the field is exist only within the axis of the solenoid. Since the field produced outside is weak and negligible when compared to the axis of the solenoid. This is the axis of the solenoid, so which may form the loop like this. So we will elaborately discuss about the properties of field lines in the next chapter, but you just see that a current carrying solenoid will simply behaves like a bar magnet. That and all we will discuss in the next chapter. But for here, we can say that the magnetic field is strong and uniform. Uniform means they are parallel lines. So uniform within the axis of the solenoid, when compared to the outer side. And since the field are very weak when compared to the inner field, so that may be negligible. Now what I am going to discuss is, as we consider here as to be the Amperian loop. So here also I can consider an Amperian loop. Say this is the Amperian loop. Say for example P, Q, R and S. So I am taking the loop direction has to be in anti-clockwise direction. Just to identify the theta value. here the dl vector, you just assume the small portion as to be dl here. The dl vector is in this direction and the magnetic field also along this direction. Therefore, between P and Q, theta will be as 0 degree. But in the case of the segments Q and R, B is horizontal. This is your B vector and dl vector is in upward direction. Therefore, theta will be 90. Yes, here the theta will be, yes, this is the dl direction, magnetic field will be like this here upward. Yes, so in this case, even though the theta may be non-zero value, because cos 90 is 0 but cos 0 is 1. So here cos 0 1, here cos 90 is 0. So here also the cos value will not be 0, but the magnetic field lying outside of the solenoid is very weak or approximated as to be 0. So therefore here B out has to be 0. So here also, as we said here, the theta will be 90 degree for this segment SP. Therefore cos theta value becomes 0. Therefore this line integral B dot dl can be classified or divided as 4 segments. That is a line integral from P to Q. So P to Q, the corresponding is B dot dl. Yes, this is the splitting of this line integral. Yes. So now please see that, as we said, B dot dl is nothing but BDL is cos theta. So BDL cos theta, and here cos theta 0, cos 0 is 1. Therefore I can directly write this. This has to be BDL plus here cos 90 is 0. Therefore that dot product will be from Q to R, the dot product will be 0, because B dot cos 90 is obviously 0. So therefore I can say that BDL cos 90 is 0. Plus you just see that the outside B out will be 0. Therefore the line integral, so plus the line integral is for example it is from R to S. So now you please see that R to S. Therefore here B out will be 0 as when compared to other parameters. So obviously it will be 0 only. So dl as cos value is either as 1 or something. So here it will be 0. Again as a line integral of S to P also will be 0 because of theta as 90. So the only the present component is this part only. Therefore I can say that the line integral of B dot dl, that is nothing but integral B to Q is B dl. So in this small region, as we said, along the axis of the solenoid, the field is constant. Therefore B into the length of this segment is taken as to be SL. Therefore once you evaluate this, you can get this has to be B into L. So this is what, children, B dot dl value. Say this is for example equation number 1. So what is the total current enclosed by the system? So I enclosed. So I enclosed is nothing but number of turns in the total current. Number of turns into what, children? The total current. So from this N be the total number of turns. Therefore the total current I enclosed is nothing but N into I, where I is current through the single turn. When I is what, children? Current through the single turn. Therefore from this we can write that it is a small n L into I. Say this is equation number 2. As per the Amperes circuital law, that BDL is equal to mu naught I enclosed. Therefore I can compare these two. So therefore B into L, that is equal to small n L I into, this is the total current, into mu naught I enclosed. Therefore I can get that B is equal to mu naught small n I. So this is the expression for what, children? Magnetic field due to a infinite long current carrying solenoid. Again, how to find the direction of the magnetic field? As we said here, in the case of circular loop, you just apply the right hand palm rule. Hold the solenoid in right hand and fingers gives the direction of the current flow, and the thumb will gives the direction of the magnetic field. So accordingly we can use that. So here, since we put that has to be outward direction, that means the magnetic field is going along this direction. Therefore according to right hand a palm rule, and this will be inward, and this will be what, children? outward directions. So please be careful with the applications of your Amperes circuital law as well as the right hand palm rule to find the direction of the magnetic field. Students, please kindly note down the notes. So that is the second application of the Biot Savarts law. So now please see that the another one, the third one is so that is toroid. Yes, since we may see that it may not be there, but please see that this is a very important application. But MCQ all must we know. So therefore toroid. So toroid is nothing but a closed circular shape form of a solenoid. So let us consider this will be the current carrying solenoid, and it is will be like this. So this is the current, some current I is going and the same current I is coming out. Okay, so now please see that three regions are considered. This is the Amperian loop 1, and this is the Amperian loop passing through the axis of the solenoid, and the another one is the Amperian loop which is lying outside of the solenoid. So this is the third Amperian loop. Okay, yes. So this is region 1 and region 2, and this is region 3. So as we said, in region 1 it is not enclosed, this Amperian loop is not enclosed any current, therefore I enclosed is 0. Therefore here I can say that B1 is 0. The magnetic field at the region 1 will be 0, since I enclosed is what, children? 0. But in the case of B3 also 0. So why B3 also 0? Since it is enclosed the whole solenoid means, in as we said, if you are considering the as a single turn, the upper part the current may be coming outward, and that lower part the current may be inward. So the outer current is positive, means inner current will be negative, as we discussed in the sign convention. Therefore the total current enclosed by the Ampere loop will be 0. Due to that, we can say that here also is I enclosed is 0, the reason what we said. But in case of B2, the field will not be 0. The field will not be 0, children. Why? Means it enclosed only one part of the turn, that is lower part means lower part, or upper part means upper part. Therefore all the currents within the particular part, lower part means all the currents are positive, or if it is outward all the currents are positive, or inward means all the currents are negative. But anyway the total current will not be 0. Therefore the magnetic field due to this solenoid, the toroid, is very similar to the solenoid, whose value is given by mu naught Ni. But there is a slight change. What is N definition in solenoid? Means number of turns, capital N by L. So here in general N is equal to what, children? Capital N by L. But here L is what is that? Length of the solenoid, but the solenoid is made in the form of circular loop. So that instead of that L represents here circumference of the solenoid. So therefore we can say that the circular path, okay, shape. Therefore here L is here, so we can say that here L is nothing but 2 pi r, where r is called mean radius from the center. So mean radius from the center. Therefore we can say that B is equal to the toroid magnetic field. Yes, B is equal to mu naught small ni, that is equal to mu naught capital N divided by 2 pi r into what, children? Yes, I. So this is the a result of the magnetic field due to the what, children? The current carrying toroid. So what is the difference or benefit of the toroid? Means which will produce the strong uniform magnetic field, and there is no leakage of magnetic field. Okay. As we discussed in capacitors, capacitor means whenever the dielectric is inserted, the capacitance increases dielectric constant times. So similarly here also, B medium, that means the hollow space is filled by any magnetic material, then B medium is equal to mu r. There we said epsilon r, relative permittivity in a capacitor, here relative permeability, so into B r. So this is the, since mu naught means we are consider air medium only, air core solenoid or air core toroid, yes, like this. And this is a relative is permeability, that and all we discuss in the next chapter. So relative permeability. Okay, students. So therefore B medium is greater than B air. Okay. So that is the thing what we must know. The another important application is there. That is a very important question for your exam point of view. Now you see that if you are considering a current carrying wire where the current is uniformly distributed over the cross section of the conductor. So let us assume that is the very important question. Yes, so that is the fourth application of the Amperes circuital law. There is a current carrying wire, yes, but the current is not distributed over the surface. Current is distributed throughout this area of cross section. So let us consider this is the area of cross section. Now the current is distributed throughout its area. So therefore, so this is the current direction. For example, the current is going like this. So current I is going like this throughout the conductor. In these cases where the current is distributed in a straight infinite long wire, we are assuming that the current is just over the surface. Therefore, the total current is I itself. But here the current is distributed through the cross-sectional area. Whenever such type of distributions are coming, so just use the elemental ratio concept, that is I total, the total current through the conductor. So I total divided by area total, that is total area. So area total, that is equal to I enclosed divided by area enclosed. Since there is a uniform distribution, therefore such type of things can possible. Therefore, we can say that, yes, from this I can say that I enclosed is equal to the total area. So let us consider the area of the wire has to be capital R. So therefore, I can say that the total current is I. Therefore, I enclosed is equal to total current I into area enclosed. So area enclosed divided by area total. Okay, children. So just see that. Therefore, I enclosed, that is equal to I into area enclosed. Let us consider that has to be some pi into small r, where small r is radius of the Amperian loop, what we consider. Therefore, I can say that small r square divided by what, children? Capital R square. This is I enclosed equation. So this is very important for the discussion. Now we please come to the derivation. Let us consider 3 Amperian loop. One is outside of the wire. So this is Amperian loop 3. One is on the wire. So the Amperian loop is on the wire. This is the second Amperian loop. So this is the axis of the wire. So this is the axis of the wire. And the third Amperian loop is within the wire. This is the third Amperian loop. So this is the third one. This may be considered to be first one. So this is the say for example R in, and this is R and this will be R out. So now please see that for the Amperian loop is which is less than 0. So that means small r, this r is not 0 with respect to this axis. R is not, small r is not equal to 0, but small r is less than capital R, total radius. Therefore, we can write this is inside point B in. Okay, now please see that as we discussed in the circuital law, as we said, so BDL, so B dot DL here, that will be B into 2 pi R circumference. So here, so we can say that for this small Amperian loop, we can say that B in into 2 pi small r, that is equal to I enclosed by that. Since the total current is not enclosed by this Amperian loop, because the current is distributed throughout the area of cross section. Therefore, I can write that mu naught I enclosed. So I enclosed we already calculated here. Therefore, we can say that B in 2 pi small r, that is equal to mu naught, that I enclosed is nothing but I into small r square divided by what, children? Capital R square. So this gets cancelled out. Therefore, I can get the result as so B in, that is equal to mu naught I small r divided by 2 pi into capital R square. So this is the expression what we get. So from this we can say that B in is proportional to R, okay, until that reaches the top surface. Now please see that the second case, this is the case 1, and the second case is, you just consider, now please see that suppose R is equal to capital R, R is equal to capital R. So if small r is equal to capital R, that is we are measuring a magnetic field on the surface of the conductor. Therefore, we can say that as we said here, or here you just substitute small r equal to capital R, you just substitute, we can get B on. So this capital R, one capital R gets cancelled out. Therefore, mu naught I divided by what, children? 2 pi capital R. So for the given wire of radius capital R, this will be constant, since we said that current flow will be steady. Therefore, this value will be what, children? Constant. Now we please go to the third case. What the third case represents means, just see, so now the third one is what, children? If small r is greater than capital R, that is outside point. So we are going to measure the B out. So outside point we are going to measure. So now please see that when we consider the outside, the total current enclosed by the Amperian loop is the total current throughout the conductor I. Therefore, we can say that B into 2 pi small r, where small r means the radius of this Amperian loop. So B out into 2 pi r, that is equal to mu naught total current enclosed, since it is enclosed the total conductor. Therefore, from this we can get B out that is equal to mu naught I divided by 2 pi small r, which is very similar to our infinite long straight conductor result. Therefore, I can say that as B out is inversely proportional to R, B in is proportional to R, B on is constant. So therefore, when you draw the graph for this, so this is small r, certain region it is directly proportional. So directly proportional, this is B in proportional to R, and when small r is equal to capital R, that will be a constant. That value is given mu naught I by as 2 pi capital R. When it is outside, they are inversely proportional, so that will be like this. So this is R greater than R, and B out is inversely proportional to what, children? Smaller. So this is the information about the magnetic field due to the a current carrying wire, where the current is distributed over the surface of the or cross section of the wire. Okay, so these are the important 4 applications of the Amperes circuital law. Yes, so very easy and very effective method to find the magnetic field due to any current carrying system by the concept of symmetry. Now please see that the another one what we are going to discuss is it's up to this the application of Amperes circuital law is over. The another topic what we are going to discuss is force between two infinite long wire. Force between two infinite long what, children? Current carrying wire. So I am just writing in short form. So force between two infinite long current carrying wires. Infinite long current carrying wires. So now please see that it's very simple. We have to remember 2 concepts here. One is magnetic field due to a straight wire, infinite long straight wire, and the second one is, as we discussed in the previous session, whenever current carrying conductor placed in magnetic field, it experiences the force due to the magnetic field. F is equal to BIL sin theta. So 2 concepts you have to be remember here. So let us consider this is the wire or its infinite long as a straight wire which carrying the current I1 at a distance d. As it produces the magnetic field. As we said here, you just find this is the position vector D. So current DL vector is like this. This is the position vector. We know that IDL cos theta. So DL vector is turns towards the R vector. Therefore, the rotation will be clockwise. So the magnetic field will be normally inward. So therefore, the magnetic field produced by the wire 1 will be normally inward, and that value is taken as to be B1. Therefore, I can say that the magnetic field due to the first wire B1 is equal to mu naught I1 divided by 2 pi D, as we discussed earlier. Okay, this is the magnetic field due to a infinite long straight wire at a point S which is at a distance D. Now, in this inward magnetic field, now what I am going to do means I will keep a second wire. A second wire which carries the current, say for example I2. Now this current carrying wire is placed in this magnetic field, uniform magnetic field. Therefore, we can say that this wire experiences some force. So therefore, the force on second wire. Why? Due to the presence of magnetic field produced by the first wire. So second wire by the first wire is given by F, say for example F21, force on 2 by 1. So F21 equal to BIL sin theta. This is the formula what we learned. So here B is what? That is produced by the first one. So B1. What is the current carrying conductor of current? That is B2. I2. So it just considers some portion of length L. So where L be the length of that portion what we consider. So therefore, you just apply here, then we can get that so therefore F21 that is equal to B1 value is there, you just substitute. So mu naught I1 I2 divided by 2 pi D into L. So this is the, now you have to find out what is the direction of force F21 force on second wire due to the first wire. As we discussed in the Fleming left hand rule, you just see that magnetic field, 4-finger magnetic field, this will be as a current direction, the thumb will give the direction of the force. Now please see that the magnetic field at this region is normally inward and the current is going upward direction. Therefore, the force acting on this second wire is towards the left side. Yes. Therefore, this is the direction of F21, the force on second wire due to the first one. So similarly, in the same way, you just approach. First you take the second wire, find its corresponding magnetic field, then you keep the first wire over there and do the same process. We can get that. So force on first wire due to second wire, that is F12, that is equal to the field produced here is B2. The wire kept at the point is I1 of length L. Therefore, here also we can write mu naught I1 I2 L divided by what, students? As D. So this is F12 and this is towards left. So the direction of the force is towards left. Okay. Now towards left. So here again is same. Yes. Since this is the right side point, so the field is inward. This is the left side point. For this wire, current is going upward. This is the measuring point. So this will be yes anti-clockwise rotation. Yes, by using a right hand thumb rule, if the rotation, that current element rotation will be yes anti-clockwise, then the field direction will be normally outward. So at this point, the magnetic field due to the second wire will be normally outward, and this is B2. So how to find the direction of magnetic field here, I will say for your confirmation. So this is the wire carrying some current I, this is some measuring point. So what you have to do, you just bend the wire toward the measuring point, in the direction of current. Now you are getting what type of rotation? Clockwise rotation. So clockwise rotation, take the right hand palm rule. So clockwise rotation means what? The thumb is normally inward. So this is the way how to find the direction of magnetic field. If the same measuring point P is left side, this will be anti-clockwise rotation. Anti-clockwise means normally outward. So that is the thing what we mentioned here. Okay, so this will be outward. So for your understanding purpose. Now please see that. So this is towards towards left, and again you apply the same thing. So the current is upward, the middle finger is upward, and this magnetic field is outward direction. Therefore, the thumb will be towards right. So this is the direction of your F12. Okay. So therefore, this will be towards right. Towards what, children? Right. Okay. So by this, you see that one conductor is trying to move like this, the another conductor is trying to move like this. So what kind of force will be there? Means attraction will be there. So therefore, by magnitude wise, the direction wise, one is towards left and another one is towards right. They are equal and opposite. Therefore, I can say that F12 vector, that is equal to minus of F21 vector. So this is the thing. Or magnitude wise, both are same. By seeing this, or we can say that F12 is equal to F21. Yes, this is the thing what we must learn. Okay. So the another important thing is, as we said earlier, the currents are in the same direction. So current are in the same direction as attraction, and currents are in the opposite direction, repulsion will be there. Okay. So that is the thing what you have to be keep in mind. Attraction will be there. Okay. So the another thing related to this one is, we just see that we can make the 1 ampere definition. 1 ampere definition here. So let us consider, since they are magnitude wise equal, therefore I can say that F is equal to F by L. This is small f. Sometimes they may given as to be small f, force per unit length, that is equal to mu naught I1 I2 divided by 2 pi d. So let us assume that d has to be 1 meter and I1 and I2 are in unit value. Say that value has to be 1 ampere. Then what we can get is small f is equal to, that is capital F by L. So mu naught value is 4 pi into 10 to the power of minus 7, 1 into 1 divided by 2 pi, the distance has to be 1 meter. So therefore we can get that F is equal to is 2 into 10 to the power of minus 7. This F is nothing but force by length, therefore Newton per meter. So whenever if you are considering two infinite long current carrying straight wire which are separated by a distance 1 meter apart in air or vacuum, there is a force per unit length. The force of either attraction or repulsion will be is equal to 2 into 10 to the power of minus 7 Newton per meter. Then the amount of current passing through the wire is considered to be 1 ampere. So this is the definition for what, children? 1 ampere definition. So this is the another important is a concept related to that. Then another one what I am going to discuss is magnetic moment. So a small definition, yes. So I can say here the another one is magnetic moment. Like our dipole moment, what we said there is there we said the product of is magnitude of charge and the distance is called what is that electric dipole moment. Similarly, we can define that one is for your magnetic system also, like bar magnet. But here we are considering about the current carrying system. For this case, how to define magnetic moment means the magnetic moment M vector, that is nothing but total current into area vector. Total current into what, children? Area vector. So it is a vector quantity. It is a vector quantity, and the unit is SI unit is ampere meter square. Ampere what, children? Meter square. As we said earlier, there are many rules to give the directions. You please take care of that. So here you just see that how to find the direction of M vector. So just again right hand thumb rule. Yes. Let us consider this will be the direction of the current in a circular current carrying wire or loop. Then as we said, you just apply the right hand as thumb rule here. The thumb points the upward direction when the current is represented by the curling fingers. So in this case, the direction of M vector is outward normal. This is the ring. So the finger is curling finger represents the current direction. Then thumb will give us the direction of M vector. Okay. So as we said earlier, the area vector is always outward normal. Outward normal, as we discussed in the Gauss law for electrostatics. So this is the way how to find the direction of the M vector, or in scalar form the same can be written as M is equal to I total or I net, you can consider, into area. So your area is that may be circular coil means pi r square, rectangular means length into breadth, something like that. Okay. So this is the another information related to what, children? Magnetic moment. The another one is another concept. Any current carrying loop or a coil or loop which may be behaves very similar to a bar magnet. A current carrying circular loop or circular coil or current carrying solenoid, all the current carrying system will behaves very similar to a bar magnet. So how to prove this one is, I will take the very simple expression. So for a bar magnet, the axial magnetic field. What is the axial magnetic field? Equatorial magnetic field. In electrostatics, we discussed electric field due to a dipole along the axis and the equatorial line. Similar way, we can discuss in chapter 5 magnetism also. So just for an analogy, I am just taking the result. The B axial for the bar magnet is nothing but mu naught 2m divided by 4 pi x cube. This is the magnetic field produced on the at a point P on the axis of the bar magnet. So this is some point P on the axis of this B axis, mu naught 2m divided by 4 pi x cube, where m is called magnetic dipole moment of the bar magnet. So similarly, for the circular coil, you just take the children. So we are already discussed there. we get B is equal to, for a circular coil, B is equal to mu naught Ni R square divided by 2 into x square plus what children? R square, where x is the measuring point. As we said, this will be SO, this is the distance x. So here we have to assume that x is greater than r. That means the measuring point is very far away from the circular coil. Then this small capital R can be neglected. So 3 by 2 will be there. Please see that this negligence will be applicable only for addition or subtraction term, not for any other parameters in product or division. Therefore, I can get that B is equal to, for the circular coil, so x is greater than r square, r is neglected, then I can get x power is a cube I will get. Therefore, mu naught Ni r square divided by 2 into what children? X cube will be there. So now what I am going to do is, I am just multiplying by 2 pi and divided by 2 pi. Just do this work, multiply by 2 pi divided by 2 pi. Then what I will get is, so B is equal to mu naught 4 pi, like a proportionality constant, into Ni into pi r square. I am just rearranging the terms, into 2 divided by x cube, where Ni is total current. Ni is what children? Total current, where N is number of turns in the circular loop or coil. So total current. Pi r square is nothing but area. So total current area. Total current area, that is nothing but is magnetic moment. So therefore, the whole term can be replaced as you just see that, yes, now you see that, or we can compare these results. So we see that 2 is there, mu naught by 4 pi, mu naught by 4 pi is there, 2 is there, x cube is there. In the place of m, what is there? Ni into pi r square. So therefore we can say that by comparing these two results, axial field due to the bar magnet and axial field due to the circular coil, we can say that m is equal to Ni into what children? Pi r square. This Ni is nothing but the total current, and pi r square is nothing but A. Therefore we can say that m is equal to I net into A. That means the result of current carrying circular coil or loop is very similar to the result of a bar magnet. Therefore we can state that from this discussion we can say that any current carrying either as a circular coil or loop or solenoid is equivalent to as a bar magnet. Suppose the bar magnet is suspended along the north-south direction or is suspended freely in a vertical plane, we can say that it is aligned towards the geographic north-south direction roughly. So similarly, whenever a current carrying coil is free to rotate, then it is aligned in the direction of as a geographic north-south. So we can say that all the current carrying circular loop or coil or solenoid is very similar to what is that called children? Yes, a bar magnet. So this is the theory part what discussed today. So kindly note down the theory part, students.